Hello, I've had several questions about U-substitution, so I've picked out 4 examples. I'm just going to work through them one by one. So here's my first example, and what I see is a function inside of a function. So what's jumping out to me is that this 2x cubed plus 5 is inside of that cubing function. And also what my mind is thinking is that if I do the derivative of this, it's going to be an x squared, and I see an x squared sitting out here. So that's driving my decision to let u equal 2x cubed plus 5. And then I do the derivative of u with respect to x, and I get 6x squared. And then I move that dx over, so I get 6x squared dx. And it's here that I stop and I map out a plan for what I'm going to do. So I see that this 2x cubed plus 5 is right here, so that's going to be u. So all of that will be u. And then the other parts that need replacing is this 18x cubed dx. What I've got sitting here is 6x squared dx. So what I need to do is multiply by 3 in order to get an exact match between this and this. So what that tells me is I'm going to multiply by 3, and this becomes 3 du equals 18x squared dx. And now I have an exact match. This, letter for letter, number for number, says exactly this. So that whole box right here is going to be replaced with a 3 du. It's going to be inserted right there. When I put all that together with my integral, I'm going to have this gets replaced with the u, so u cubed. And what this box gets replaced with is 3 du. I'm going to put the 3 on the outside and the du to end the integral. And what I've done is I've taken a very complicated integrand and I've turned it into something very simple. So now I just have to work with this antiderivative here. And I just do a power rule. So add 1 to the power, divide by the new power, and then my plus c. And then I just go back to my original variable. So this 2x cubed plus 5 that I started with now goes back in for that u. And I get my final answer is 2x cubed plus 5 to the 4th over 4 plus c. And that is my answer. And then on to the next one. So this one's got a nice little exponential for you, but it's going to follow pretty close to what the other one did. So I see that I've got this e to the 3x minus 2 inside of this 5th power function. So I'm going to let u equal my inside function. So I'm going to let u equal e to the 3x minus 2. And du dx equals an exponential derivative is you write down what you see times derivative of the exponent. That minus 2 just drops off. I get du equals 3e to the 3x dx. And now I stop at this moment and I plan out how my substitution is going to go. So I know that this e to the 3x minus 2 is going to be u. So this whole piece right here, everything in there is going to be a u. And what I have left to replace is a 6e to the 3x dx. What I have going for me is a 3e to the 3x dx. So what that means to me to get this over here to match what I'm trying to replace, it's going to require multiplying by 2. So I'm going to multiply both sides of this times 2. And now this becomes 2 du equals 6e to the 3x dx. And now I have an exact replacement. So this 6e to the 3x dx matches this exactly. So I'm going to replace that box with 2 du. And now when I put all that together, it's going to say the integral u to the 5th. And then this whole box is being replaced with a 2 du. Pull the constant multiple to the outside and end that integral with a du. And now I'm just did a simple power rule. So I'm going to add 1 to the power, divide by the new power, plus c. That simplifies to 1/3. Put your original u back in. So e to the 3x minus 2 to the 6th power plus c. And then this is my final answer. The next question has a little trig in it. And again, what I'm looking for on this one is an inside function. And I see this x to the 5th plus 4 is inside of that sine function. And I also know that when I do its derivative, I'm going to get something to the 4th power. And I see that 4th power sitting here, which means that's probably a good direction to go. So u equals x to the 5th plus 4, du equals 5x to the 4th dx. And I just put the dx on the other side right away. And then I start mapping out my replacement. So I see this x to the 5th plus 4 is right here. So I know that that part is going to be replaced with u. So all of this is going to be a u. And then the other parts that need replacing is 25x to the 4th dx. What I've got going for me is 5x to the 4th dx. So it means I'm going to have to multiply by 5 to get that exact match. So multiply both sides by 5. So times 5 on this side, times 5 on that side. And that's going to give me 5 du is my replacement for 25x to the 4th dx. So now all of this 25x to the 4th and dx is going to get replaced with a 5 du. And when I put all that together, my integral looks like sine of u, and then the 25x to the 4th and the dx gets replaced with a 5 du. And now I'm ready to do my antiderivative. Just one thing, when you're sitting at this step, you want a complete and total conversion to this new variable of u. You don't want x's and u's in the same problem. So you need to convert it totally and work with that. So now the antiderivative of sine is negative cosine u plus c. And now I just have to get this back to my original variable. So in place of this u, I go back to that x to the 5th plus 4. So negative 5 cosine of x to the 5th plus 4 plus c. And that is my antiderivative. And also keep in mind that any of these antiderivatives can be checked by just doing a derivative. And this last question is a little more theoretical. So I'm given that f prime of x, capital F prime of x, equals lowercase f of x. There's different ways to approach this, but I think what I want to do is rewrite this integral 1 to 3. If f and capital F prime are the same, I can rewrite this as big F prime of 3x dx. And then I see that this 3x is an inside function. So 3x is inside of that f prime. And when you have a function inside of a function, that composite function, that means I need a U-substitution. So I'm going to let u equal 3x, du equals 3 dx. And what I've got a replacement for is just a dx, yet this says 3 dx. So what that tells me is I need to multiply both sides by 1/3. So now this is going to say the integral f prime of u, and then the dx replacement is 1/3 du, so I have 1/3 du. Also keep in mind that these limits are going to change. So this one is a definite integral, unlike the other ones we looked at. I've got my limits here. And when I switch from the x variable to the u variable, when I make this change from x to u, I need to change these limits. And I change them by plugging them into my u equals equation. So the 1 and the 3 are the limits for the x variable For the u variable, I need to change them. So when I plug the 1 into u, my new lower limit is a 3. And when I plug a 3 in, my new upper limit is a 9. And now the antiderivative of f prime is just f. So I get 1/3 big F of u from 3 to 9, limit shift to the end. This is what I used here is FTOC part 1. And now I just plug in each one of these. So I got 1/3 f of 9 minus 1/3 big F of 3. And these are capital F's here, not that lowercase f. So these have to be capital F's.